My background is I came more from the research world, but a couple of years ago, I started to get really interested in what it takes for the research that we were working on to actually get adopted in the real world, and that led me to discover how important infrastructure and developer tooling can be for like the adoption of some of the algorithms that we were thinking about. And so I've shifted over to mainly focusing on tooling and infrastructure for the past year or so. So working on a new startup, we're not really talking publicly too much about what we're doing yet, but it's related to some of the ideas that we'll talk about today. So if it's of interest to you, I'm happy to chat more about it. So this talk is going to be in three parts. So first thing I'm going to do is talk about my view of sort of where we're going as a field in machine learning. And then I'm going to talk about kind of what's going on in the machine learning infrastructure world and to what degree that sort of supports the direction that the field is going overall. And then last, I'm going to propose a concept that to me is sort of one of the missing links in the machine learning infrastructure stack and could help address a lot of what makes machine learning infrastructure hard currently. So diving into my view of where we're heading as a field in machine learning, I guess, to put it concretely, the place I think we're going as a field, and I think where we already are now to some degree, is that machine learning is now very rapidly becoming a product engineering discipline. Okay, so it's not just me saying this. Elon Musk agrees with me, so we're in good company here. And so I want to talk a little bit about the history of machine learning in industry and give a view on how we got to this point that we're at today, with machine learning becoming a product engineering discipline. So let's go back in time to the 2000s. Machine learning, was not nearly as popular as it is today, but it was already being run in production in a lot of companies. And the way that machine learning was typically used is that what I would call like machine learning as analytics. And so machine learning as analytics is kind of characterized by, simple models that are being trained on like kind of medium or maybe relatively large data sets. But they're being run offline and they're being used to produce reports, right? And so the value that you as a company get from running machine learning in the analytics context is by taking a model and then incorporating the insights from that model into your decision-making process. So something funny happened in the 2010s, and that was the deep learning explosion and the beginning of the machine learning hype era. And in this era, a lot of companies started to adopt machine learning, maybe not because they had a really concrete sense of what it was going to get them in the near term, but because it seemed like an exciting technology, right? Like a thing that was going to drive like future strategic value for their business. And the way I would characterize this era is sort of, a lot of the value that companies were getting out of machine learning in this era, like generously, you can say it was sort of from the marketing potential of, having researchers, having an R&D team that are working on stuff that is like exciting and can be used to convince future hires or future investors that machine learning is something that you're really good at. But I think what's changing is that there's cracks that are starting to form in this like machine learning hype era. And I think we're starting to enter a phase where machine learning projects are going to be judged by the same criteria that every other project in a company is judged by, which is whether those projects actually generate value for the underlying business. And so where I hope that we're going as a field is entering an era where like what I would call like a machine learning driven product era, where the main focuses are on reproducibility and scalability and maintainability, more so than necessarily like having the most complex and most state-of-the-art methods. And the way that value to the organization is measured is by whether the models that we're building actually make our company's products and services better. Okay. So that's where I think we're going, or where I hope that we're going. And the challenge that this presents is that if you want to actually build machine learning enabled products as opposed to just machine learning research projects, it requires a fundamentally different process than what I think most machine learning teams are used to following. So this is kind of how I would characterize the process that a typical machine learning team might follow. So you select a problem, you collect some data about that problem, you clean and label that data. Maybe that part takes a lot of time. And then you train a model, you iterate on that process, you keep training better and better models to fit the data set that you collected. And then eventually you have a model that's kind of good enough according to some criteria, and you use that to produce a report. And then you're done, right? So I would characterize this process as sort of what I've been calling flat Earth machine learning. And so the reason why I call it flat Earth machine learning is that it kind of reminds me of like how, people who think the Earth is flat just thinks that like, yeah, there's nothing over the horizon because I can't see it, right? So that means that that's the end of the world. I think similarly, like just because you don't see that it's really that like your data is changing from under you and you need to collect more data and use that to refine the model doesn't mean that you don't need to. And so I think like if you actually want to succeed at building machine learning enabled products, the things that you need to add to your process is essentially this outer loop, right? And so, once you have a model that is good enough according to some criteria, then you need to test that model across all of the metrics and slices of data that you care about. You need to deploy that model into production. When it's in production, you need to monitor it to make sure that it's still performing as well as it was when you first deployed it. And then you need to close the loop by collecting the data that's going through the model, cleaning and relabeling that data, and then retraining a new version of the model on the new data. And so fundamentally, the reason why this is necessary is that data, like models, tend to get worse over time when they're in production because data distributions tend to change because the world changes and because your models actually might have some influence on that. But when this is done well, on the other hand, like this actually creates a really powerful loop in the models that you're creating, which is called like a data flywheel. And so the idea of a data flywheel is that as your model gets better, then that makes your product better. And as your product gets better, that gets you more users. Those more users get you more data. And then the more data allows you to make the model even better. So that kind of positive virtuous cycle is called a data flywheel. And that's, I think, one of the main goals that you should be trying to achieve if you're trying to build machine learning enabled products. So one other point I want to make on this is that, unfortunately, I think that machine learning teams that aren't able to navigate this transition are not going to do very well over the next 10 years. So a couple of data points to back that up. There's been a couple of like kind of high profile, like let's say less than super exciting exits for very hypey, kind of fundamentally research oriented machine learning groups like Uber ATG and Element AI that, a couple of years ago were sort of examples that everyone was pointing to of like really, really cutting edge machine learning work, but only a few years later kind of exited at less than exciting multiples. Even OpenAI, I think, which you could argue is one of the biggest beneficiaries of the AI hype era, has sort of seen the writing on the wall here. And they're, I mean, maybe pivoting is too strong a word, but they're redirecting themselves toward being a product organization and productizing some of the models that they're creating, like GPT-3. And then, maybe for many of you, I think like kind of the more concerning thing here is when you talk to industrial firms that have been trying to pilot machine learning systems, the results so far have not been that good. And I think like maybe one of the most worrying statistics from this industry report, which I can send a link to, is that like a full 20% of companies freely admitted on the survey that really peer pressure was one of the main reasons that they invested in AI to begin with. And so I think this really just points to like kind of an era where machine learning wasn't scrutinized to the same degree that other parts of companies were. And this is something that's going to have to change. So what does it mean for you, right? I assume many of you are machine learning engineers or working in the field right now. So one implication of this is that I think other disciplines, other than just training models, are going to catch up to model training in prestige and pay. So I think the last kind of 5 years was sort of a golden era for people who are really good at training machine learning models, where you could, where those folks have like command massive salaries, and it was sort of the most prestigious job in the field for a while. But I think that that's not going to be true forever. And then, if your team is sort of measuring your output by like what I would call the 3 Ps, right? So, papers and pie charts and proofs of concept, going forward, I think that's no longer going to be enough. The flip side of this is that I think there's actually a massive opportunity for teams that do make the transition to have a ton of impact. And so one kind of nuance that I'll put on that is that I think like when a lot of people think about the impact of machine learning in the real world, they think about sort of a few really high profile use cases that hopefully will happen and will be very transformative if they do, like autonomous vehicles and translation and drug discovery, these sort of like world changing moments almost, if they can be made to work. But I think that one thing that's actually really underrated about the impact of machine learning is the long tail of machine learning applications. So just the, what I would call like the MLification of everything, right? Like I think in 10 or 20 years, pretty much every product or service that we interact with is going to have machine learning embedded into it to some degree, right? Just like how most products and services that we interact with today have software making them better at some point of the chain. And I think that this the like long tail of machine learning applications is super underrated. And I mean, just as a simple example, a couple of years ago, I saw this couple of weeks ago, actually, I saw this article, I believe from Dropbox, about how they use machine learning to save almost $2 million a year on document previews, right? And I think that there's just dozens and dozens of these stories of companies that are just using machine learning to make everything that they do more efficient, more personalized, and more automated, and that's going to continue. Okay, so let's start thinking about like if we believe that this transition needs to happen, then what are the implications for the infrastructure and tools that we use to build machine learning systems? So to start having that conversation, I'm going to lay out sort of what I see as being some of the salient differences between kind of offline analytics or hype-driven machine learning and machine learning enabled products. And so not every ML product will have all of these things, but these are like some of the characteristics that can describe them. So unlike kind of analytics-driven ML, ML products often need to run online in real time. You can't make the assumption for ML products that the data distribution is going to be always going to be the same as the one that you train on. In the real world, data distributions evolve constantly, and so our systems need to be able to deal with that. We also can't just assume that like the data distribution that we're training on is something that's relatively easy to measure using a small test set, right? In the real world, a lot of distributions that we care about, like self-driving cars, for example, the data distributions themselves are super messy, and there's a long tail of edge cases that we actually really care about. And then, unlike in kind of like analytics-driven ML, where there's always a human that's using the prediction of the model as an input to their own decision making, so kind of this like slow feedback loop. In machine learning enabled products, oftentimes we want our machine learning systems themselves to be able to make predictions autonomously, or even just semi-autonomously, but like having a tighter feedback loop where they have to be correct more often. And so these differences imply demands for ops and infrastructure that didn't exist before, right? So we need to be able to host and serve models with low latency. We need to be able to deal with these constantly evolving data distributions by frequently retraining models, or maybe even continuously retraining our models. We need to be able to inspect our data in a scalable way and manage all the slices and kind of edge cases and subsegments of our data that we care about to deal with this long tail real world distributions. And then we need to be able to quickly catch and diagnose bugs and distribution changes as the data evolves, right? Because since we're making predictions autonomously or semi-autonomously, there isn't always going to be a human to catch when the model starts doing something fishy. All right, so next thing I want to do is I want to kind of walk through this loop and take a look at some of what's happening in the infrastructure world and talk about where I think maybe some of the gaps are. So so starting from training, I think that the training piece of the infrastructure stack is like definitely the best served piece right now. So there's a few kind of categories of tools that are emerging here. There's training infrastructure tools, PyTorch Lightning, Determined AI. There's experiment management tools that help you deal with the larger and larger number of experiments that you have as you start moving onto more complex ML use cases, weights and biases, TensorBoard. And there's tools for producing reproducible pipelines, right? So if since we need to retrain our models frequently in machine learning product world, being able to reproduce something that we did before becomes increasingly important. So I think that this part of the stack, there's still a lot of improvements that can be made, but I see this as sort of being relatively well served. All right, so moving on to the testing part of the infrastructure. So there's a couple of tools that are emerging here. So there's one around what I would call like model performance exploration. So the logo on the right is the what if tool from Google, which I think is sort of maybe the best known example of this. Weights and biases has some features for this. And then there's a category called around like model explainability, Fiddler, Arthur, Terrera, a few sort of exciting tools there that help you try to understand why the model is making the predictions that it made. You have CI/CD tools for actually operationalizing these tests that you're running. And here I just have like traditional CI/CD tools, which do an okay job of transferring over to machine learning workloads, but maybe you're not super optimized for it. But there's a few things here that I think people complain about pretty regularly that are still hard. So one thing that's still hard is just understanding where it is that my model is performing poorly. So across, like, I can look at my validation score, and maybe that validation score is good. But that doesn't necessarily mean that the model is performing well across all of the like parts of our data that we care about. And so finding the parts where it's performing poorly is still a pretty hard problem. And then I think there's also an infrastructure challenge here that as typically as you scale up the complexity of your models and your data sets that you're working on as a team, what teams end up creating is sort of this like matrix of test cases for their model. So like lots of kind of smaller data sets or like slices of data sets. And eventually this will end up becoming hundreds or thousands of data sets that you want to perform well on. And then you care about performance of like potentially many models and many metrics against each of those smaller data sets or subsets of your data. And so this starts to become a challenging infrastructure problem as you scale that up. Okay, so moving on from testing to actually deploying of models. Few categories of tools that are emerging here. There's model serving tools, Cortex, Seldon, Algorithmia, and then the tools that are being developed by the cloud companies. There's a category called feature stores, and I think there's a lot of confusion about feature stores. Maybe you all will be very familiar with this probably, but the oversimplification I would make of feature stores is that like one of the main value props is to make features available for prediction in real time. So that's kind of why I put them in the deployment category. They also help with other stuff. But there's a few things in deployment that are also still hard, right? So one thing I think that's challenging for a lot of teams is doing experimentation at this stage. So ideally, when you deploy a model into production, a new version of your model, let's say, you don't want to just immediately start sending all of your production traffic to that model. You want to run a shadow test or an A/B test to make sure that the new version of the model actually performs better. And that can be pretty challenging for a lot of teams. And then making sure that the model is actually consistent between the offline world and the online world. Feature stores help with this for feature definitions, but there's still a lot of bugs that occur when you're translating a model that you built offline, like let's say in TensorFlow, to something that's actually going to run online. All right, so you've deployed your model into production. The next thing that you need to do is monitor it and make sure that it's still performing well as your data distribution changes. So there's some tools that are emerging that help you detect kind of data quality issues or data drift issues. DQ, TensorFlow Extended, TFX, data validation, and Great Expectations are three open source tools there that are gaining some popularity. And then you have your traditional system monitoring tools like Datadog, which are helpful for understanding, for monitoring your machine learning system in production, but are not enough because they really only tell you about system metrics. But there's a couple of big challenges that remain here. One thing is that, like measuring data drift is not really what you care about when you're monitoring the performance of your model. Data can drift without actually affecting the quality of your model. And so what you really want to do in a perfect world is to measure the performance of your model in production. So to actually, take the feedback that you're getting about your model's predictions, whether that's from labelers or, or potentially like users clicking on your thing or business metrics, and then correlating those with model performance. That's still a challenge for a lot of companies, and the kind of data quality tools don't really help with it. And then detecting drift itself, TFX and DQ and Great Expectations do this a little bit, but drift detection is still a bit of an art, particularly for high dimensional data like images or text. All right, so moving on to trying to close the loop by collecting new data. So, you need to put your data somewhere, and data lakes and data warehouses are typically where that data ends up. But what's still challenging for a lot of teams to figure out is, for a lot of ML use cases, this isn't specific to ML, but you can't necessarily store all the data that is going through your models. So deciding which subset of your data you want to store is still a hard problem. And then another challenge for a lot of teams is connecting that data back to the model, right? So for a particular data point that you're storing in your data warehouse, how do we know if this data point is one that we care about? Like if this is one where the model didn't perform well on, or this is one that we should use for retraining. So cleaning and labeling that data, there's a bunch of tools that are emerging to help you label your data. There's tools and services. There's kind of a newer category that I'd call like active learning tools, which are helping you decide which subset of your data should you retrain on. But there's still some big challenges in this piece. So deciding what data you should actually label and what data you should train on once you've labeled it are, I think, like both unsolved research problems and places where the tooling is not yet that mature. And then lastly, closing the loop back to training. One thing that's still really hard for a lot of companies to figure out is just knowing when I should retrain, right? So when does the cost reward benefit make sense to retrain my model? And then there's like an emerging challenge, which I think is like not even really on the horizon for most companies, but retraining models online, which is still extremely difficult, but I think not something that most companies should be doing yet. Okay, so let's try to synthesize kind of what we saw as some of the gaps here, right? So one of the takeaways I have from this is just there's a lot, right? Like there are many tools that are emerging to help address some of the problems that emerge when you do machine learning product engineering. But there are a lot of problems that still exist, right? So one of the categories where problems still exist is at the boundaries of these tools, right? Especially anything that shepherds data through this whole process. So if you have, if you have data going through your model, you care about that data because that will also help you train a future version of the model. And so how do you make sure that a data point that, maybe caused you some problems in production makes it all the way back into your training cycle, for example? And then lastly, like one other takeaway is that at each of these stages, so at the kind of testing and evaluation stage, at the deployment stage, at the monitoring stage, and at the data collection stage, having a granular understanding of model performance. So understanding your model performance across all of the slices and metrics that you care about is kind of lacking and is a really important signal to use to make decisions about moving your model and moving the data that feeds your model through the operational lifecycle of the model. Okay, so that's kind of a whirlwind tour of the production machine learning landscape and what I see as some of the gaps. And so the next thing I want to talk about is an idea that I think could help address some of these gaps and hopefully bring more cohesion to this kind of relatively fragmented tooling landscape. So the idea that I'm going to talk about is what I've been calling the evaluation store. And so what the evaluation store, the way I would define it is it's a central place to both store and also query metrics. And these metrics are both for the online world, so for your model that's actually running in production, and also the offline world, so models that you're evaluating before you deploy them. And the metrics that we're evaluating are meant to estimate how like the quality of your model, both in like kind of a ground truth way, so when you have access to good labels, but also in an approximate way. So when you don't actually have access to good high fidelity labels. So I'll unpack this a little bit. So what does this actually look like? Like what's going into the evaluation store and what's coming out of it? So I'll break this down by the stage of like model development and deployment. So in training, what goes into the evaluation store is profiles of the data that you're training the model on and the predictions that are coming out of it. At the evaluation stage, what you put into the eval store is definitions that you create of metrics and slices of data that you care about, as well as feedback on the model predictions. So your labels, essentially. And then in production, what goes into the model is Again, profiles of the data and the predictions that are going through your model in production. And then where you have them, also feedback on the way that the model is performing in production. And then one other thing to note here is, I think the evaluation store is like distinct in my mind from your model hub or your feature store, but it should talk to both of those things, right? So your evaluation store should know about all the versions of your model in your model hub, so it can associate model performance with a particular version. And I'll talk a little bit more in a couple of minutes about the difference between what I'm proposing here and the way that feature stores work. Okay, so that's kind of what goes into the evaluation store. So how do you actually get information out of it? So what does a query of the evaluation store look like? So you'll query a subset of models, a subset of metrics, a subset of slices, so of like subsets of your data that you care about, and then some specification of the window of data that you want to run this query across. So is it like recent data? Is it a particular evaluation run? A couple of examples. You might want to know, like, what is the average drift across all of my features in my production model? And can we do this in a way that's importance weighted? So we like care more about features that are important to model predictive performance. So it's kind of a monitoring query. You might also want to know, how much worse is my accuracy in the last 7 days than it was during training? So another type of monitoring query. Or how do all of my metrics compare for these two models across all the main slices in my main evaluation set? So kind of a classic like testing query. But you could also run an A/B testing type query here too. Okay, so that's sort of a bit of a description of kind of what the evaluation store does, what goes into it, and what you can get out of it. I want to do a quick digression here to talk about a term that I've used a couple of times, which is approximate performance metrics. So what do I mean by that? Well, I think like one cause of confusion in the like machine learning monitoring world is that there's all these sort of things that you're told that you're supposed to care about, like drift and outlier detection and all these algorithms for computing those things. But if we step back and think about monitoring models and understanding their real world performance from first principles, the thing that we really care about in a perfect world, we would basically have instantaneous labels on all of our predictions, because then we could just tell exactly how well our model is performing on all data points seen in production, and that kind of answers our question. The reason why we need to care about things like data drift is because in the real world, labels are not always that easy to come by. And so approximate performance metrics are basically any way to guess at which data points might have had poor performance before you actually get to see the label. So examples are, distribution distance between like this window of data points and some reference distribution, outlier detection. But it could also be things like weak supervision, kind of in the snorkel sense, if you're familiar with that. Or it also could be metrics about your users, like user engagement or something that's not actually really the predictive performance of your model, but is maybe a proxy for it. Okay, next thing I want to talk about is kind of how the evaluation store fits into the life cycle of kind of model deployment, maintenance, and retraining. So starting from training, the way that the evaluation store interacts with your training process is that you will register the data distribution and performance for the model as you train it. But then what the value that you get out of the evaluation store at the training stage is that we can compare the training data that you're sending in to recent production data. And we can warn you like, hey, looks like this data that you're training on looks really different from production data. So maybe there's a bug either in production or in training with how you're generating your features. At test time, the main thing that you'll take from your testing process into the evaluation store is performance of your model across all of the test slices that you care about. But the evaluation store will also be a helpful input to the testing process in that it'll allow you to pull historical data that's been flagged as interesting. So maybe there's some data that gave a previous model trouble that you always want to test on. And then also the evaluation store could be how you store slice definitions. So as those definitions evolve, like maybe the product manager decides that we want to define this slice differently, then that'll automatically get updated into your testing process. In the deployment stage, your deployed model would have to kind of log the approximate performance of the model on all of your test data back into the evaluation store. But what the evaluation store will allow you to do is easily run like a shadow test or an A/B test, which would actually just be a query of the evaluation store. Monitoring is maybe the most straightforward application of the eval store. So you could just fire an alert whenever the approximate performance of your model on any of the slices that we care about dips below some threshold that we define. And then at the data collection phase, we might want to sample more data that our approximate performance metrics tell us is unlikely that the model performed well, or we just don't know how well the model performed. And similarly with the labeling phase, right? So you might want to label data that where we think the model might perform poorly. And then finally, the evaluation store can tell you when to retrain your model, because simple criteria would be just retrain your model when your approximate performance dips below some threshold. Okay, so to summarize this a little bit, what could an evaluation store help you with? One big category I think is reducing organizational friction. So increasingly, as machine learning projects get more complex and get more important to the businesses that are developing them, there's more and more stakeholders that are involved in the model creation process. So you have your ML researcher that trained the model, and then you have the ML engineer that deployed it. But increasingly, you also have maybe an ML ops team or an ML platform team. You might have a PM, you might have a business stakeholder. And so one important function that this could play is getting all of those stakeholders on the same page about what are the metrics we care about, what slices of data do we want to evaluate them on, and what does good look like? Like what are our tolerances? Could also help you deploy models more confidently. So since the evaluation store works across the offline world and the online world, across testing and production, you know that you'll be evaluating your metrics and slices consistently in testing and prod. And also those metrics will be surfaced to stakeholders. So everyone will have can basically look at what the evaluation store says the model is doing, so that they know at any given point in time how well things are performing. Catch production bugs faster. So one of the nice things about this is that it could help you catch degradations, not just in aggregate, but also across slices that you care about, and then sort of drill down into the data that caused that. Can help you reduce cost, right? So right now, I think the most common strategy that companies have for reducing data labeling costs and data collection costs is just randomly subsampling data that's going through their models. That's highly suboptimal. You actually want to, there's some data that goes through your model is much more informative in terms of evaluating model performance or training a new version of the model than other is. And this could help reduce those types of costs. And then lastly, and I think to me, maybe most importantly, as a machine learning researcher, is that a tool like this could actually really help you make your models better, right? Because it can help you make decisions like, when should I retrain this model? Or what data should I use to retrain it on? That ultimately have a big impact on the performance of your model in the long term. All right, one thing you might be wondering is, I've heard a lot about feature stores, right? So shouldn't this evaluation thing just be part of that? I think the answer is pretty clearly no. And the argument I would make for why is that the feature store is indexed by feature, right? So the unit of study in a feature store is a feature. Whereas in an evaluation store, the unit of study is a model. And a couple of reasons why that's important. So a model, just because your model has one feature as an input, it doesn't mean that it actually looks at the entire distribution of that feature. So there could be some bias to when the model is actually taking that feature as an input. That means that it's only actually looking at a subset of the distribution of that feature. So drift at a feature level doesn't necessarily mean that is not necessarily the same as drift at the input level to a model. But maybe more importantly, a poor quality feature, so a feature that is different distribution, has different effects on different models. So for one model, that might be the single most important feature. And for another model, it might be kind of an unimportant feature. So if a feature drifts, you actually really care about which model you're studying in order to tell whether that drift is significant or not. I think also like one thing that is maybe not a lot of folks are discussing is that I think like the feature store, I think is going to become is already a really important part of how a lot of teams build their machine learning systems, but it doesn't make sense for all of the data that you're looking at in your model to come through the feature store. So for example, typically feature stores aren't really used for the requests that are coming directly from users or really high dimensional data like images or text. And so we still need to be able to monitor those inputs to the model, even though they're not coming from the feature store. So I don't think these are independent concepts. I think that they should be integrated with one another and they should talk to each other. But I don't think that you should rely on the feature store for doing all of your model evaluation. Another question you might have is like, hang on a second. I feel like we're just talking about machine learning monitoring here. Like, why do we need a different name for this? So isn't this just machine learning monitoring? And the answer is, yeah, this is just machine learning monitoring. The hard part of what we're proposing here is approximating how well your model might be performing right now. Right? And so that is exactly the question that we talk about when we're studying machine learning monitoring. But the answer to this is also no, right? So, and there's a couple of reasons for that. So the evaluations, like when we talk about monitoring, it's kind of an online performance estimation thing. But the evaluation store also should provide a consistent view between offline and online, right? So let's learn from our mistakes, like our previous mistakes in the field of machine learning engineering, right? A huge source of engineering complexity and bugs is consistency between the offline world that's kind of generated by the people training the models and the online world that's generated by the people productionizing the models. It's one huge reason why feature stores are becoming so popular, right? So let's not repeat our mistakes as model evaluation gets more complex and have like two separate pipelines for offline evaluation and online evaluation. So other big difference between like, I think how people typically think of monitoring and the evaluation store is that the evaluation store should be really tightly integrated into the entire MLOps stack. So there's a lot of moving pieces here that need to be consistent, right? The evaluation store should be used to make decisions that move models and data throughout their operational lifecycle. And then lastly, the evaluation store doesn't just keep track of performance, but it also links that back to what data caused questionable performance, so that data can be used in future testing and retraining, right? So in the monitoring paradigm, you really just see aggregate performance, and you can't easily link that back to the data that caused it. So maybe one way to kind of like visually articulate what I'm arguing for here is that when I think of monitoring, this is sort of like the system diagram, right? It's like you deploy your model into production, and then you have a monitoring system that sits on top of it and looks at the production data. But the evaluation store sits actually like in the middle of your entire ML infrastructure stack and has a two-way sort of communication at each phase of your ML infrastructure. All right, so next thing I want to talk about is, this is not just like an idea that I like made up in my head, and I'm not the only one who's been thinking about this. So I want to talk about a couple of case studies really quickly about other companies that are doing something that has this flavor. So I think the most concrete one is the Tesla data engine, which I would highly recommend like trying to find a talk. I think there's a link to a talk here by Andre Karpathy about how Tesla approaches data set curation and data collection and performance evaluation. But at a very high level, Tesla has an infrastructure that allows them to deploy arbitrary like monitoring hooks onto their vehicles that run alongside the production models and help them catch things that are likely to be inaccuracies in model performance. And what that allows them to do is target their data collection and target their evaluation process towards those inaccuracies. An example of an open source system that I think does a lot of what I'm proposing here is TFX data validation. So this is a system diagram. I won't go into details here because it's obviously a little bit messy. The thing I really like here is that they propose a consistent data validation system between training and testing, and between offline and online. The thing I think is missing relative to what I am proposing is that there isn't really a mechanism here for incorporating feedback on model performance into your model evaluation. And feedback about model performance, when you can get it, which you can't always get it, but when you can, is the best way of estimating how well your model should be doing. And the other thing I think is missing from TFX data validation is that there isn't a tie back between your evaluation of model performance and the particular data points that caused issues. So like when TFX data validation system runs into a problem, it just fires an alert. It doesn't point you to the individual data points that might have caused it. And then the last case study that I'll talk, I guess I'll just very briefly talk about is the Overton system from Apple. So this is, I think, is a very underrated paper that I would highly recommend checking out if you're interested in machine learning infrastructure. It was created by some of the creators of the Snorkel system for weak supervision. And it has a pretty mature way of users defining labeling functions and slices of data that they're going to perform evaluation on. And so that's the thing I really like about this system. All right, so to summarize what we covered today. So in order for machine learning to become a product engineering discipline, what we really need to create is an infrastructure stack that helps teams create a data flywheel. So create these self-reinforcing systems that get better over time instead of worse, which is typically what happens to machine learning models. And so we talked about a lot of the tools that are out there, and we identified a few things that are still missing. And the main categories that we talked about are having a granular kind of offline and online understanding of how well your model is really performing, and orchestrating data and models throughout the entire loop of the model development and deployment and monitoring and retraining process. And so the question I'll leave you with is, maybe an evaluation store could help with this. And so I'll pause there. I'm happy to answer any questions. Yeah, and I think, like I mentioned at the beginning, this is very closely related to some of the stuff that we're working on at our new company. And so if you're interested in, potentially trying to build a system like this at your company, then come talk to us.
This is a great, Josh, great, fantastic talk. And I, now in my next presentation to my boss, and I can see, well, the ML is a product engineering, so I can borrow some of the phrases here. I do have one question, kind of a follow-up here comparison with the entity store to the evaluation store. So I'm basically, I'm comparing the ML's like experimentation results, like for example, the weight and biases or the ML flows, who also store the metrics which compare different model performance. It's a subset of what you're doing. So what here you're basically centralized, essentially almost like you create a metric store which just for machine learning models, essentially have a data lake for machine learning training or whole process. So this is centralized the metrics, but the ML flow and the weight biases and other experimental results, they register the model and they also record all the experimentations on the different. So it's kind of a subset of what you're doing. So suppose I have to use both. So where I store my metrics?
Yeah, so is the question like, what's the relationship between a system like this and your experimentation platform?
Yeah, but and also so where the metrics I'm going to store, because I got two places. One is say for example I'm using MLflow and I have experimentation results there related to the model and related to data, and then your evaluation store. So where can I put my stuff?
Yeah, so I think that there's definitely some overlap between these two categories. I think there's maybe less than it seems like at face value, because they're really solving different problems. So experiment management tools are like really useful when, and I use these tools a lot when I was back when I was training a lot of machine learning models, but when you're kind of going through this experimentation process of iterating on what model best fits your data set, there's a lot of information that you want to look at to try to debug why is this model not training as well as I thought it was going to train? Which hyperparameters are best, things like that. Then where this tool starts to come in is when you have a candidate model, right? Like when you have a model that you think might be, okay, this could be our next production model. And so the types of metrics that you're storing here are a little bit different, right? Like in evaluation store, you don't really care about learning curves per se. But what you do care about is like evaluation across all the subsets, like all of the subsets of data that you care about, which is not something that you typically study in an experimentation platform, right? Like those are more focused on like metrics that allow you to kind of distinguish between models during a rapid experimentation process. And typically you wouldn't run like your full evaluation pipeline on models during your experimentation process anyway. So I would say that like I think the single source of truth should depend on which part of the process you're talking about. Like I think you still need to have a log and like a registry of all of your experimentation results. And so this is almost like that, but for your productions, like for the models that you're actually deciding whether to put into production. And so there definitely needs to be a link between them, because you don't want to introduce inconsistency when you decide to promote a particular model. But I think it's hopefully it should become relatively clear which metrics go into which category.
Got it. Thank you. So I think we have a few questions in the Q&A section. So there's a gentleman, Dan Son, posed 3 questions. So the first one is, how's the structure of testing part like in the entire process of our machine learning system? What's the differences between monitoring and testing? I guess you addressed some of the questions, so you can probably answer again.
Yeah, I mean, I would say like very simply, monitoring testing for machine learning systems are maybe not all that different. Like in both cases, you're trying to answer the question of like, in this like matrix of slices, like data sets or slices on one axis and metrics on the other axis, how do I fill in all the boxes in that matrix? Same thing you're trying to answer in monitoring. The distinction is that monitoring is online data, testing is offline data. And that's not just a semantic distinction. The really important thing there is that that means that in the online world, you typically don't actually have access to ground truth, at least not right away. And so it's important to also be able to estimate how well the model should be performing across each of those categories, even though you don't have access to labels.
Next question is also from Dan. Said it's in terms of a human in the loop feedback, what specific problems that needs more our focus, other than concept, like for example, data drift, any rule to follow to build this kind of loop?
Well, I mean, I think there's a couple of other like high level things. Maybe the most salient one is active learning, right? So how do you decide which subset of your data you should label, which subset of your data you should train on? Yeah, not sure if that answers the question. Maybe Dan, if you want to clarify a little bit.
Okay, well, let Dan clarify, post on the question again. Let me continue with the other question he has, Dan. So once we get the feedback from the online model performance, that is now, we know the model is performing poorly on those data, then how are we going to update the model based on all these feedbacks? Any specific directions we're looking into?
Yeah, so I mean, at a very, very high level, right? Like the way that you want to update your model based on feedback is, turn the feedback into labels, take your production data, incorporate them to a new training set, retrain your model and redeploy it. Now, there's a lot of steps there that make that relatively complex because you need to actually figure out how to turn the feedback into labels. You need to collect the data and store it somewhere just operationally. You need to decide which subset of the data to retrain on. You need to actually orchestrate that retraining. And then you need to make sure that the model that you retrained on is actually good enough to go into production. So it's tricky. Like there's still a lot of things you need to get right there, but that's kind of the high level way I would think about it, is like store the data, use the feedback to get labels and retrain on the new label data.
Cool. Next question from Hamid. He said, how do you deal with the PI data in your evaluation store? How do you prevent the leakage of the PI data? The question applies to any sensitive data from production, transaction systems, that you collect.
Yeah, I feel like this is more of like an implementation specific question than like a conceptual question. So I can't really answer this yet. Yeah.
And next one is from Deep. He says, can you share the slides?
Oh, sure. Yeah, I'll put them on my Twitter after this.
Okay, okay. You can send me the link. I can share on the meetup, and so they can get it.
Okay.
Okay, cool. Any other questions? So have Josh here. Any other questions that are related to the talk and or any other machine learning infrastructure and other related questions? I totally can see that I can use this evaluation store because I totally can see that will fit in the right of one of the almost like say, hey, I need a table to get all the stuff to reevaluating how's our performance or historically during a different phase of the production or trainings, and I can see how which what has been making more effect or worse effect, and I'll just kind of for just like any other data, we want to see the the trendings and or what have been making the impact, and just totally I can totally see that.
Yeah, absolutely. I think there's a lot of maybe that's another way of answering the question that you asked, right? Which is that like evaluation is more like the kind of like the object in a experiment management platform is like an experiment, right? So it's a particular training run on a particular like fixed data set. Whereas in an evaluation store, you're looking at a model and then you're looking at that performance across time.
Right.
And there might be many different data sets that go through that model, both offline and online. And so you want to be able to kind of like flip the axis and look at and be able to query performance, not just for the specific training run, but across like any of the data that you care about.
Right. And then you probably have subdimensions related to and see which one contributing to the performance changes or whatever. Yeah, totally I can see that. Okay, Dan posed the question again. Let's see, how do you see the future of the machine or deep learning in the next 5-10 years, and which direction it would move forward?
Oh yeah, this is a broad question. I mean, I think this talk is like largely maybe my main answer to that question, which is that I think the most important thing for us to get right as a field now is not research. I think that like research is still very, very important. And I'm still very optimistic about the acceleration of research over the next 5 or 10 years. But I think that like the downside case for machine learning as a field over the next 5 or 10 years is that all of these really promising research ideas never lead to as much value as everyone in the field thinks that they're going to. But the upside case for the field in the next 5 to 10 years is that machine learning becomes ubiquitous and really just becomes part of everything. And so that's I think to me the most important question in the field right now. There's a lot of exciting research areas as well. I think unsupervised learning, semi-supervised learning, really exciting. For example, I think machine learning being applied to more like scientific disciplines is really exciting. So there's a lot of like interesting questions to explore there if you're more interested in the research side as well. But yeah.
Cool. So there's one more question from Meet, and he posted it on the chat instead of the Q&A. So, so he said, how do you link the evaluation store to Apache Native open source project, which is lineage and training data associated with it? So actually, I think that's driven by the Nessie, the project, open source project, driven by the Dremel company. Actually, I was just talking to him the other day. He's going to give a talk probably late April on the Nessie project. But maybe you can address this question.
Oh yeah, I don't know that project, so I don't know yet.
So like a Git, like a Git commit for the data. So and I think the first implementation is on AWS DynamoDB, and with all the everything is GitLab. So I don't know.
Is it like DVC or like something like that?
To some degree. So I'm not too familiar with it. I just exposed that recently. So but anyway, if somebody else would probably know more. Okay, so there's another question. What do you think about auto ML tools? Do you think that all those processing and deploying pipeline could be automated at a certain point?
Oh, yeah, I think auto ML tools are great. I mean, I think it's good. I think one general trend over the next 5 or 10 years is just going to be, I think I sort of alluded to this, but it's going to be like the growing relative unimportance of being good at training models. So I actually think that, being like people who are really good at training models are going to be more important to companies in 5 or 10 years than they are now. But as like a slice of the value that's being created by machine learning, it's going to be a much smaller part of the pie. And there's a few things that are driving that. Auto ML is one of them, right? Like auto ML is like kind of works for some fields now, I would say. Another one is like just the better like tools and libraries and stuff that we have for training models, Hugging Face, PyTorch Lightning, those sorts of things. A third is the rise of what I would call like mega APIs. So GPT-3 is sort of the main example of that now, but I was actually personally really surprised when GPT-3 came out even though I had seen, versions of it before, at how broadly applicable that single model was. And so I think more and more machine learning use cases are going to be eaten by these mega APIs where, some companies spent 10 or 20 or $100 million training the single model. And so it doesn't make economic sense to do anything other than fine tune this model that someone else already created. So that's a third reason that I think model training is going to be less important. But I think like as model training becomes less important, the rest of the pie is going to become more important to get right. I think there's some hope that for some models, the rest of the kind of loop can be automated as well. So, if you have a relatively mature system, you might be able to just like automatically collect data that's going through your model, like feed that to a labeling service, retrain the model, make sure it passed your tests, redeploy it. And so I think there's some hope for like fully autonomous machine learning systems like that. But I think there's still a lot of work that needs to happen before then. There's some pretty big unsolved problems. So I think that like the more realistic vision of the future in the medium term is that there's kind of a role that starts to emerge, which I would call like a model operator. And the way I'd articulate that job is it's sort of like a data analyst who focuses on machine learning models, right? So your job is to understand the data that's going through the models really, really well, and then understand the process of building and training machine learning models at enough that you can kind of babysit this. Babysit's not the right term, but you can like guide the learning of the model over time towards like better and better models by curating the data that's going into the models. And so these folks are going to spend their time like understanding model performance, understanding how model performance relates to data, sampling data, sending data off to be labeled, helping managing the labelers and stuff like that, but aren't necessarily going to be experts in model architecture and things like that.
Great. I think that's the last question we have. And I would like Josh and spend all these times for this fantastic talk. If Josh have no objection, we're going to share the videos after we edited the recording, and then share on the YouTube link. And Josh, you can send me the slides, and I'll share the link as well there.
Okay.
Yeah. Okay. Great. Thank you so much, Josh. And we also want to thank Bill from the AI camps, and he provide the provide the Zoom room link for us. So of course we thank you everybody else and to attend this for this fantastic talks. So my name is Chester Chen. I will see you next time. Okay, bye bye.